All right, in this case, though, just like the last one, it's a simple parabola. So just do a rough sketch. All right, so 0, 0. Well, I need to go out to 2. So 1, 2. This is where 4 is going to be. 2, 3, 1. So we're looking at something like this. All right, but I have to break it up into 8 subintervals. All right, so n is equal to 8, so that's our 8 subintervals. I have 2 subintervals so far. Cut them in half. I'll have 4 subintervals like the last question. All right, I'm going to label them up while I'm here. So this would be 1/2, 3 halves. And then I'm going to chop each of those intervals in half. All right, so that's going to give you 1/4, 3/4, 5/4, 7/4. All right, and so we just verify that there's 8 regions there. All right, and it looks like there is. So when we go to look for our delta x, I mean, if you have to draw the diagram, you've already figured out what delta x is. It's b minus a over n, but in order to come up with all of those subintervals, we had to inherently figure out what each interval was worth. So whether you do it with the formula or if you do it by the diagram, either way you're going to come up with 1/4. So 2 minus 0 over 8 would be 1/4. Now when we generalize this will become more important, right? Because when you're doing it numerically, it's easy. I mean, you're just breaking it up into 8 intervals, right? So, I mean, when I'm creating a scale, I go by half spaces. So, like the total space I wanted to be 4, I knew half of that would be 2, half again would be 1, and then I have my scale. All right, same idea on the horizontal axis. So you don't need advanced level calculus to figure that out. You just need, just some common sense, I guess. All right, but we do have to determine some rectangles that would make sense depending on the situation. Left to right, again, is we want the vertex, the upper left-hand vertex of the rectangle to be on the curve itself. So I'm going to draw my rectangles going from left to right. Now left rectangle approximation is not always going to give you an underestimate, but for this problem and the last one, that's how it's been working out, and that's because of the nature of the function. All right, so it has to do with the concavity. So because this is concave up, the left rectangles end up being, left rectangular approximation ends up generating rectangles that are below the curve. But if it was concave down, they would be above the curve. Right? So it's interesting when you think of it that way. Anyway, what I want are the x values for which I have a point on the curve. Okay, so sometimes it's a good idea to accentuate those points that you plotted on the curve, just to really kind of draw your eye to what you're looking for. All right, so we're starting with 0. I didn't label it, but now I did. And we're going to go all the way to 7/4. We're never going to get to the 2 because 2 corresponds with a y value that's not on the curve, right? If I'm just looking at the rectangle. So all the x values except for 2 would be in my set. So the step in the process where we plug it all into the original function, that's to find the corresponding values of y. All right, so the actual points on the curve, they have x values and y values. We have the x values, we need the y values that go along with them. So f of m sub I requires us, in this case, because it's x squared, to square each of these values. So 0, 1/16, 1/4, 9/16, 1, 25/16, 9/4, and 49/16. Then we multiply by delta x. The idea being, again, that we're looking to find the area of each of these rectangles. If I didn't give you this process and I just gave you the diagram labeled up and everything, and I said find the area of each rectangle, you'd probably do this next step on your own. Because you'd say, okay, well, how tall are they? I need to figure out what these distances are. That would come from this step. And then I'd multiply it by whatever the base is. In this case, the base is consistently 1/4. So I'm going to multiply each of these values by 1/4. So the next step in the process, again, is to take our f of m sub I values and multiply by delta x. All right, so we're looking at, I'll write it underneath, 0, 1/64, 1/16, 9/64, 1/4, 25/64, 9/16, and 49/64. So then I want to be adding all those together, right? So that's the fun part, I guess. All right, 1, 6, 15. I need 16 more of those, so 31, 56, 60, no, 56 plus 30, 66, 92. Ah, geez, I lost it. Is it 141 over 64? Yeah? Oh. Cool. Huh. I'm not just saying that, right? It really is that. Get my calculator also. I hear a lot of non-committal. 35 over 16?
140 over 16.
What, 40 over 16? Son of a gunhead. Over 16. All right. So then we would do the same thing, but for rectangles coming in from the right. All right. So we'll go back to the diagram and mark it up. And then after this, we'll be able to generalize it so that we don't have to do all this work all the time. But it may sound weird, but they always ask a rectangular approximation question on the AP.
This kind of question?
Like something like this, yeah.
Let's go with that.
It's not always structured the same way. Sometimes it's, you know, like given as a table, where they actually give you a table of values that represent the rectangles, and then you have to figure out what the approximated areas would be. So they kind of streamline it a little bit, so you're not going through all this stuff. I think out of selfish reasons on their end, because it would take forever to grade something like this. But the general idea is always there. All right. So anyway, it looks like I'm using every value except for 0 now. So the m sub I would be 1/4, 1/2, 3/4, 1, 5/4, 3/2, 7/4, and 2. All right. If we evaluate them all, we're going to get the same stuff that we had for the other side, except we're going to throw on a 4 at the end. I already screwed that up. 1/16, 1/4, 9/16, 1, 25/16, 9/4, 49/16, and 4. All right, so far it looks like our sum is going to be 4 more than what it was before because we're replacing a 0 with a 4. But we also have to multiply by delta x. So each one of these values is going to get multiplied by 1/4. So 1/64, 1/16, 9/64, 1/4, 25/64, 9/16, 49/64, and 1. All right, so then when I go to find the sum here, I'm not going to reinvent the wheel. I mean, that's too late, I guess. Yeah, 51/16. We're just adding 1 to the previous answer. We're adding 16/16 to it. Because we know that the only difference between our array of values in blue and in red is that we have the additional 1. Just tack it on. So we know that the area is somewhere between 35/16 and 51/16. All right, so 35/16 and 51/16. Now, we can get some decimal values for those. 35/16 is roughly 2.19, and 51/16 is roughly 3.19. All right. Now, if we reflect back to what we did yesterday, and you can look on your own. What was it? 7/4 and 11/4, something like that. This is a narrower interval. All right. That interval was a little bit wider. This interval is a little bit narrower. All right. So what seems to be happening is as I increase the number of subintervals, I'm closing in on the true area underneath the curve. Right? And so that's really what the goal is, because now the follow-up question would be, who wants to do all this for n equals 1632 or 256? Not many people, but your program is happy to do it for you. Right? So if you put a very large value for n into that rectangles program, it just feels weird saying rex. I don't like it. But if you were to put in something like, put in the 256, put in 512, put in something really large for n, you're going to have an infinitesimal difference between your LRAM, your left rectangular approximation method is the M part, and your RRAM. So that's the general idea. So what we get from this is the idea that if we can make the n value as large as possible, we'll get the true area under the curve. So if n were to approach infinity through a limit, we can take our summation and make it as accurate as it could be. Okay, so that's where we're going with this.